Hello, I will talk about special relativity. There are three phenomena that occurs when someone is traveling at very high speed, close to the speed of light. The first phenomenon is the increase in mass. The second is length contraction, and the third phenomenon is time dilation. I will start with the increase in mass. Suppose the twin brother who goes on a journey in space weighs 98 kilograms, so his mass will be 10 kilograms. According to the simple equation, weight equals to the mass times g. G is the gravity on Earth, that is 9.8 meters per second square. So when we divide 98 by the gravity, that is 9.8 meters per second square, we get the mass that equals 10 kilograms. So the mass of the twin brother on Earth is 10 kilograms. He weighs 98 kilograms on Earth, and his mass on Earth is 10 kilograms. I will explain the meaning of G equals to 9.8 meters per second squared. If you drop an object from the roof of a high-rise building, the velocity of the object will be 9.8 meters per second in the first second, and in the second second its velocity will double, and it will be 19.6 meters per second. In the third second, the velocity of the object will be 3 times of the velocity in the first second, that is 29.4 meters per second, and so forth. In the 10th second, its velocity will be 98 meters per second. In conclusion, every second the velocity of the object will increase by 9.8 meters per second. So that is the meaning of the gravity on Earth. Okay, so according to the mass increase equation of special relativity, his mass in space will be about 16.33 kilograms, but he will not feel it. First of all, I will explain the equation of mass increase. M is the mass of the object when the object is traveling at very high speed in space, and m naught is the rest mass, that is to say the mass of the object on Earth. In our example, the mass of the twin brother on Earth is 10 kilograms. So we divide m naught by the root of 1 minus v squared divided by c squared. V is the velocity of the mass of the object that travels in space at very high speed. and v square is velocity, and we divided it by the speed of mass squared. So in our example, the mass of the twin brother on Earth is 10 kilograms, and his mass on Earth will increase to 16.33 kilograms. Okay, we actually divided the mass on Earth by the root of 1 minus his velocity in the spaceship in space when it travels towards the star epsilon, and we square his velocity, and we divided it by the speed of light squared, and we get that his mass in the spaceship when he is traveling at the velocity of 240,000 kilometers per second is 16.33 kilograms. But he himself will not feel that his mass has been increased. Okay? And if his twin brother has a mass detector, the detector will measure 16.33 kilograms. That means that his mass has increased by 63.3%. Okay, now I will talk about the second phenomenon that occurs when someone travels at space at very high speed. The phenomenon is length contraction, or shortening the distance. Shortening of the distance. When you measure a distance between two objects that are not in motion relative to each other, let's assume that you measure a certain distance. So that distance will shrink when one of them moves at a speed very close to the speed of light relative to the other. And in our example, the distance between Earth and the star epsilon is 10 light years when you measure it on Earth. And actually you should remember that our sun is not moving relative to the star epsilon, because the sun and the star epsilon move as one unit around the center of the galaxy, but the distance between them doesn't change. Okay? Suppose that my thumb is the solar system and my finger is the star epsilon, and my fist is the center of our galaxy, that is the center of the Milky Way. The solar system and the star epsilon revolve around the center of our galaxy, the Milky Way, as one unit. So the distance between them doesn't change. The distance between the solar system and the star epsilon doesn't change because they move as one unit around the center of our galaxy, the center of Milky Way, and the distance between them doesn't change. Okay, so actually when we measure the distance from Earth between Earth and the star epsilon, in that case we can say that the distance between the sun and the star epsilon doesn't change because they move as one unit around the center of our galaxy, the center of the Milky Way. And then in that case, the distance between them is 10 light years. Okay? The distance between the sun and the star epsilon is 10 light years. But when you measure the distance from the spaceship that moves in space at a speed of 240,000 kilometers per second, then the distance will be shrunk to 6 light years only, from the point of view of the twin brother flying in the spaceship. Okay, so I will explain the equation of the contraction of distance between two objects in space. L equals to L naught times root of 1 minus V squared divided by C squared. So L is the distance between two objects in space when one of the objects is moving towards the other object in very high speed. And L is the distance between that two objects when they are not moving relative to each other. Yes, like in our example, our sun and the star epsilon are not moving relative to each other, and in this case the distance between them is 10 light years. And we multiply it by the root of 1 minus V squared divided by C squared. So in our example, as I have already said, the distance between our sun and the star epsilon is 10 light years. And so is the distance between Earth and the star epsilon, because we see our Earth as the same as our sun, because the distance between them is about 150 million kilometers. That is a small distance compared to 10 light years, yes? So the distance between Earth to star epsilon is 10 light years when they are not moving relative to each other. So we know that the Earth is revolve around the sun, but that is something that you can neglect because here we are talking about the distance of 10 light years, and for this reason you can neglect the fact that our Earth is moving around the sun, and we can see it as that the sun is not moving in compared to uh, compared to the star epsilon. As I've already said, that they are moving as one unit. They revolve around the center of our galaxy, the center of Milky Way. So the movement of the Earth around our sun is something that you can neglect. Okay, so the distance between Earth and the star epsilon is 10 light years, and we multiply it by the root of 1 minus the velocity of the spaceship that moves towards the star epsilon squared, and we divided it by the speed of light squared, and the final result is 6 light years. So we see that the distance between Earth and the star epsilon shrinked from 10 light years to 6 light years only. So that phenomenon is called the contraction of distance. Okay, so when you have two objects that one of the objects is moving towards the other objects at very high speed, in that condition you have the phenomenon of contraction of distance. So the distance between that two objects will shrink according to that equation. That is the equation of contraction of distance between two objects, that one of them is moving at very high speed towards the other objects. Okay? But in addition to that, the height of the man in the spaceship also shrinks. And if on Earth his height is 1.8 meters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spacecraft shrinks to only 1.08 meters. So I will explain the equation of the contraction of the length, or in this in our example is the contraction of the height of the twin brother that occurs when the twin brother is moving at very high speed towards the star epsilon in the space. L equals to L naught times root of 1 minus v squared divided by c squared. So you see that it is actually the same equation of contraction of distance, and here it is about the contraction of the height, or contraction of something that is moving at very high speed in the space towards the other objects. In that case, as I have already said, there will be a contraction of the object that is moving towards the other object at very high speed. And in our example, when the twin brother is traveling in the spaceship at very high speed towards the star epsilon, his height will be contracted and it will become shorter when he is moving at very high speed in the space. So L actually is the height of the object or the man that is moving towards the other object at very high speed, and L naught is the height of the object at Earth. The height of the object, or in our example, is the height of the twin brother on Earth. And we multiply it by the root of 1 minus v squared divided by c squared. V is the velocity of the object that is moving towards the other object that is moving in space. In our example, the velocity of the twin brother that is in the spaceship and moving towards the star epsilon, his velocity is 240,000 kilometers per second. So L naught is 1.8 meters. So on Earth, his height is 1.8 meters, and when you move at very high speed in the spaceship towards the star epsilon, his velocity is 1.08 meters only. So it will be shorter by 72 centimeters because of the fact that when you move at very high speed in space, you will be shorter. There is two phenomena that occurs when you are moving in space at very high speed. The distance between you and the other object will be shorter, and also you yourself will become shorter when you are moving in space at very high speed. Okay. And if the twin brother that stays on Earth had a height detector, then the detector would show a height of only 1.08 meters, but the twin brother who is in the spaceship doesn't feel that he is shorter. Okay, now I will talk about the third phenomenon that occurs when you are traveling in space at very high speed, and the third phenomenon is time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took 25 years for the twin brother to return from a journey in space, in the spaceship the total time that it passed is 15 years only. Okay? So I will explain the equation for time dilation. T is equals to T naught times root of 1 minus v squared divided by c squared. So T is the total time that is passed in the spaceship that is traveling at very high speed, and the T naught is the total time that passed on Earth during all the journey from Earth to the space and back to Earth. Okay, and we multiply it by the root of 1 minus the speed of the v squared. V is the speed of the spaceship, and we divided it by the speed of light squared. So in our example, the total time of the twin brother, yes, the total time that passed on Earth is 25 years, and we multiplied by the root of 1 minus v squared divided by c squared. The velocity of the spaceship is 240,000 kilometers per second, and when we divided it by the speed of light is 240,000 kilometers per second divided by 300,000 kilometers per second, we get 0.8 squared, and 1 minus 0.8 squared is 0.36, and the root of 0.36 is 0.6, and when we multiply 0.6 by 25, we get 15 years. So the total time that is passed in the spaceship is 15 years only, 10 years less than the total time that is passed on Earth. So from the point of view of the twin brother that is on Earth, because of the he sees his twin brother in the spaceship traveling at very high speed, there will be a time dilation. That is to say, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. And actually that is the reason that the total time that is passed on Earth is only 15 years. 10 years less than the total time that is passed on Earth. So that is from the point of view of the brother that stayed on Earth. But while from the point of view of the twin brother who embarked on a space journey towards the Epsilon star, he is at rest, and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of distance according to special relativity, and the total distance between the Earth and the star Epsilon will be 6 light years only, and the round trip distance is 12 light years, and at a speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to the contraction of the distance between the spaceship and the star Epsilon as mentioned. So from the point of view of the brother that is in the spaceship and traveling at very high speed towards the star Epsilon, he is at rest, and the star Epsilon is traveling towards him at a speed of 240,000 kilometers per second. And in this situation, there will be a contraction of distance between him and the star Epsilon, and the total distance between him and the star Epsilon will be 6 light years only. and the total journey back and forth from Earth to star Epsilon and from star Epsilon to Earth will be 12 light years. It's the total way, and when we divided it by the speed, that 80% of the speed of light, that is 240,000 kilometers per second, we get 15 years. So actually we see that the two brothers, the two twin brothers actually agreed that the total time that is passed in the spaceship is 15 years. Okay, thank you very much.